What's up, guys? It's week 6 of RoboJackets TE sessions. I'm Sarah Storer from the RoboJackets outreach team, and we are here presenting TE sessions with Brian Carlson from 6829. And this week is our 6th week, which is our computer software week, and we are working on solid principles this time around. So yeah, snaps for Brian.
Good morning. My name is Brian Carlson. I am with Geekspace Gwinnett, which is a makerspace in Gwinnett County. We do outreach, helping support FRC teams, and I'm also a mentor with Ignite Robotics 6829. And so what this talk is covering is how to write code such that you promote quality. It's real simple to do in the FRC environment. But when you start working on stuff at school, and if you're looking to go into college in programming or in the get a job doing it professionally, this kind of stuff is very much portable and is not specific to robotics. Why does my, fine, I'll just do this. Come on. So basically, why does this matter? Fundamentally, a lot of times you'll find out that people say, it works, ship it. And that's great, and that will work for that one release. But what you find is the more you do that, the more problems you're gonna have, and the more bugs you'll get. So basically, back in the early 90s, a bunch of software engineers started talking about software craftsmanship. And so I want to talk about what that was and how we got to where we're at now. They came out with a book called Design Principles, but everybody basically talks about it as the Gang of Four. These four software engineers started thinking abstractly, not worrying about the actual, how to write code. They asked questions like, how are these things similar and different? One of the things they did was they talked to some college students and gave them 20 different problems, like how would you solve these software challenges? They talked to some senior software engineers and they said, how would you solve these things? So if you put them in buckets, how many different solutions do you have? And it turned out the people in college who didn't have a lot of experience, they had like 13 or 14 different solutions for these 20 problems. And the senior software engineers had a lot fewer. So as you start working with code, if you can start seeing patterns where they may look different, and you can then collapse it down to a pattern, it does a couple different things. One is, if I have a pattern, I can give that pattern a name. So if I ask you to go write this code, and I use a name, it's very easy to communicate. One of the patterns is an adapter pattern. And so there's a lot of times what you'll find is you have some software that does something and it consumes another service, and maybe the data is in a different format, right? So I have my data, and some of that data isn't needed by the other service, so I need to have a way to change my data into that data, right? So you write an adapter. And so now I put the adapter in the middle and the two of them work. If you think about it from a real world example, if you ever have a 3-prong plug, all right, so now I'm gonna say how you could do something. Don't do this, it's not a good thing. But if you had a 3-prong plug and you wanna plug it into an old 2-prong outlet, they used to make a little adapter that you plug in the 3 prongs and 2 come out the outside, right? And you can plug it in. All that did was change how your interface worked with a different interface, all right? Nowadays, you don't want to do that. Those are grounding issues and stuff like that. But that's just in a real-world example. There's also a factory pattern. If you think of a real-life factory, if you order a car, right, I order all these options, and I give it to Chrysler or Ford or GM, and out comes a car from the factory, right? They're building different cars, but the factory doesn't know what it's doing. It's just giving back. You give me input. I ask the factory to give me a car, and then I now have the car that I want. You could do the same thing in software. So for example, you could have a factory that does, so I'm gonna start using some, let's see. You have a factory that, let's say, gives you shapes, right? So if I have a circle and I have a radius, all right, so I could say I want a circle, and the factory gives me, my shape factory gives me back a circle. But I can give it the same request, but give it different parameters. I now can get back a square or a triangle, right? So at that point, I'm not tied to creating a new circle, a new triangle. The factory just gives me what I want, all right? So I'm not coupled to that. So that was the first step, right? The Gang of Four started coming up with broad principles, right? Different design patterns. A gentleman by the name of Uncle Bob in the late 90s, early 2000s came up with basically 11 design principles for object-oriented development. And they sort of broke down into 3 different categories. One, where basically how do you design your classes? You know, it's more like the low-level code area. The second area is how do you design your packages? All this stuff is in one project. How is that put together? Called cohesion. And then finally, coupling. So when you're writing code, a lot of times we talk about cohesion and coupling, okay? So if we think about robotics, all right, cohesion means things are very narrowly focused, all right? So if, for example, you have a drivetrain that drives your wheels and it has encoders, and all of a sudden you decide to change your lift on your robot, and you have to change your drivetrain code because that drivetrain code was somehow dependent upon the lift, those two are called coupled, all right? So you do not want to have things coupled, because if they're coupled, when you change one thing, you have unintended consequences, all right? So you want to have very tight, loosely coupled, right? So two things are not tied together. And the second thing is, inside that one entity, it's very focused, all right? So for example, that drivetrain is using the subsystem of the lift. Nobody would ever expect a drivetrain to have anything related to the lift. So the focus of the drivetrain is is not very cohesive, all right? So cohesive sticks together. If you dropped all these things, think of magnets, right? All these different features, you drop them down, and they'd all come into little groups of similar function. It's very logical where it goes. That's highly cohesive. You want to be highly cohesive, loosely coupled. It gives you a lot of flexibility. So now that we got these broad things, right? So remember we talked about patterns. If I give them a name, it's easy to talk about. So Michael Feathers, after Uncle Bob came out with his 11 design principles, came up with the term SOLID. It's an acronym, and you'll see what they all stand for here in a second, but it's a single responsibility, open closed principle for O. L is the Liskov inversion principle. I is interface segregation, and D is dependency injection. So we'll talk about, the rest of this talk will be all about those letters. And so now you can talk about SOLID is the 5 kind of like core principles to keep your code well structured and easier to maintain. Before we get going into all that high level stuff, I do not assume that everybody here has programmed before. I've actually given this talk to a neighbor of mine who was a sophomore, likes the idea of programming, but never programmed. So if I just sort of give some general terms, so that way we all understand the same definitions, we'll be ready to go. So from a robotics, so first off, who's rookies to FRC? He hasn't been in FRC before. All right, great. All right, so I'm going to say things like motor controllers and coders, and you're going to like, huh? So I'm going to go over some robotics terms, and I'm going to go over some programming terms. So a drivetrain is like your car, right? When you push on the gas, it goes in your car. It's your engine, it's your transmission, and it's the frame and wheels. In robotics, it's basically the same thing. It's all the things that make your robot move. We may not know what next year's game is, but I guarantee you're going to have a drivetrain. There's something called a motor controller. All right, that's basically a little device that actually controls the motor, how fast to go, and which direction to go. So when you program, you don't actually control the motor, you control the motor controller, and it controls the motor. Additionally, pneumatics, sometimes you may use air on your robot to control things instead of electricity. We use, and you can use it possibly if you have a shifting drivetrain, you might use pneumatic to shift your gears from low to high. So also with pneumatics and FRC, you have pressure restrictions. So there's usually a pressure sensor that tells you how much pressure you have. And so those are the things that we'll be talking about in some of the examples we're going to cover. Now on to some software terms. So a class is basically a group of data or functions that are put together as a single entity, all right? So I'm gonna start using a lot of financial terms. Part of it's because for several years I did some banking applications. So you got a debit card, and for us older people, we got checks, right? So if you take a debit card, fundamentally, when you think about what a debit card payment would be, you go to the store and you put your credit card in. You have an amount, right? And if you ever noticed, you put your PIN in, it goes out, and it authorizes it. You can have that money, and then great. Turns out your money is not gone at that point in time, right? Later on that night, they will send those transactions off to the bank, and the bank says, "Oh, I reserved $5 for that purchase. I'm now going to take or debit $5 from your account that night." Okay, so if you look at that, a credit card would have that kind of information, right? But it doesn't make sense that a check would have that kind of information, right? A check, if I write a check, it also has an amount, right? But what you can do with a check is you could, that amount is basically how much is going to be debited from your account, right? But you actually can call your bank and say, "I need to stop payment on that check," right? So you can stop a payment. Well, that's something that's special to a check, all right? So a credit card, you put it in, it has an amount you're going to use, they have to authorize it, and at the end of the day, they're going to take the money out of your account. A check, you write it on a piece of paper, you mail it, you can call your bank and tell them, "Don't make that payment. I don't want it gone," all right? But when the check does come in, they'll take the money out of your account. So you can see there's a lot of similarity, okay? So you might have one class that has for a debit card and one class for a check. Inheritance. So inheritance, think of it as your family, all right? So you live at home with your parents, right? So in your house is all your stuff, right? You get access to all the stuff in the house because of your parents, right? If they pass away, you get your inheritance, right? But now you don't get everything in the house that's your parents because they say some of that stuff is just for them, right? You can't go in their bank account because that's private. But all the food in the pantry, you could have at it, all right? So if you think about it, inheritance is a relationship between two objects or entities. Some of that stuff is private, so the parents have stuff that the children can't have. The parents have stuff that the children can have, and the parents have stuff that the children can have and everybody else, all right? So for example, if you have a playground in the back, people can come to your backyard, everybody can play in the playground, right? But they're not going to be able to come in your house and eat your food, Okay? If they ask the child, hey, can I have some food, and the child gives them some, that's fine, but they do not have access to that protected stuff inside the house. And they definitely don't have access to the private bank account of the parents. Okay? So if we think about that relationship, all right, if you think about the credit cards and you think about the check, all right, they're both payments, right? People call it payment processing. So every payment needs to have an amount, right? That's the data every payment needs to have, right? But what you do is kind of different, right? A credit card and a check, you both need to take money out of somebody's account. So they got to have an ability to debit your bank account. But what's unique to a credit card is when you use it, they authorize the money right then, right? So you could have a generic payment class with two kids, one kid being a debit card that then says, I get all that stuff up there, but I also want to add the authorizability. And I write the code for that down there. A check would also inherit from a payment, but it would, all the data for how do I take the money out is up top. The data for the amount is up top. But in the actual check class, there's the ability to cancel a check, all right? So you have this thing where my function may be spread between myself and my parents, all right? So you want to sort of break it up that way. Another term, interface. An interface is basically an agreed upon contract, all right? So if you think about it, who's heard of the term of a GUI, or graphical user interface, right? It's what you see on your software, right? I can click on things, right? But I don't know what's going on behind the scenes. I know that there's a file save. I know that I can click on this thing in a game and it does something, right? So interfaces allow two different entities, in our case, classes, to communicate without actually knowing what's happening behind the scenes. So for example, when I'm doing a payment processing application, right, and I want to authorize a credit card, I just say, authorize this payment. I have no idea what's happening on the other side. I just know that there's authorization. Okay? Now, an interface does not define everything a class can do. It just defines an agreed upon set of methods, okay? So you can have more methods than what's defined in an interface. And you can actually have multiple interfaces on your classes. So if you had a save, an edit interface, and maybe you had a payment processing interface where you can settle transactions, you can use both of those where you're basically saying, I agree to provide these 4 or 5 functions, right? So we talked about interfaces, we talked about classes. So the question is, what are solid principles? Fundamentally, what you'll find is a lot of times you got to write software fast and you're trying to just get things going. And it could very much be a game of Jenga. All of a sudden, I touched something and it broke. So solid principles help us make it less brittle and more stable. The first principle is the single responsibility principle. Hold on a second real quick. So the first principle is the single responsibility principle. Basically, a class should have only one reason to change, okay? So everybody's, I talk to students about a lot of different things, but the classic example is I asked them, so you go out into the woods for 2 weeks by yourself. Do you want a Swiss Army knife, or do you want to have a 5-inch nice hunting knife? And they're like, I want the Swiss Army knife. I'm like, well, does it do anything well? No. Most of the stuff you can do with a knife, you can do with a Swiss Army knife. And somehow you could figure out if I needed to open a can, you take a knife and you can open the can. But the reason why you want one reason to change is knowing where change belongs, all right? So if you have a single responsibility, and for example, drivetrain, the drivetrain should deal with everything to make your robot move. So if somebody says, we want to add a new wheel to our drivetrain, or we want to go from, not a new wheel, we want to add a new motor to our drivetrain and go from a 2-motor to a 4-motor, or 4-motor to a 6-motor, you know where the change belongs, all right? It's very easy to figure out all the places you have, right? Because it's highly cohesive, right? My changes are in that one spot. And the example I want to give you is something that I had at work that people that have programmed a lot before will laugh at. We had an application that people could write checks, and then when the checks came in, we would check to make sure that, so they'd write a check, you'd upload the checks you wrote, and 3 days later when the checks came in, we would look to make sure the check that you wrote matched the check that you uploaded, so the amounts were the same, and we would say, good, cash the check. If they're different, we'd say, hey, is this really a mistake on your upload, or did somebody like start adding zeros to your check and is trying to defraud you? Seems real simple, all right? It's a little more complicated than that. So I came over to work on this code. The person that wrote before wasn't there anymore. Turns out it was a salesy guy that kind of knew how to code. That's always the best kind of code. The logic for all that was in one method, and it was 20 pages long. And I looked at that and I'm like, oh my God, how do I change this? It's one big monolith, right? Another example we had, one of the programmers I worked with was helping a team at a competition one time. They're like, hey, can you help us out with autonomous? And he came back, he goes, I can't fix that. The only thing I can do is if I touch that code, it will break, all right? So when you got big things, you're probably doing more than one thing, right? So drivetrain should do some simple stuff, right? It should drive, right? If you have stuff in there that doesn't belong, let's say you had for some reason, you decided to put your code for your pressure sensor, for your pneumatic system to run all your pneumatics on your robot, happen to be inside the drivetrain because maybe you're checking there for some reason, right? And all of a sudden, you're driving and your pneumatics stop working. Well, you find out, oh, why are we turning off our pneumatics when we check the pressure? We're just driving around. We're not really using the subsystem. We didn't expect that. So focus your code to do one thing, okay? So I'm going to, the next one is the single responsibility principle. This one sort of actually ties in, open-close principle. This one actually ties in well with single responsibility. This was come up with by Bertrand Meyer in 1986. Software entities should be open for extension but closed for modification, okay? So we talked about that drivetrain, that we had the single responsibility. It just drives, right? There's something called PID. So PID is a little more advanced way for all the rookies out there, a little more advanced way of controlling your robot. Instead of just saying turn the power on, turn the power off, there's some math behind it that you say drive forward 5 feet, and then it figures out how much voltage to apply to the motors to drive, okay? And so what you could do is, if we have the ability to drive, it works, okay? Now I want to add in a new function called PID, right? So right now we know we're now going to have two reasons to change, basic driving and PID. Now, so side note, with all these things, you could be really great theoretically, and you make your code really hard to maintain because you have so many small pieces. It's hard to maintain, right? So there's a balancing act. So I'm using the drivetrain and PID as an example. You may choose not to do it based on what you're doing in your code. But so theoretically, if I had a drivetrain that drove, all it does is joysticks and it goes forward, right? Now I want to push a button and have it drive forward 5 feet. And I want to use PID to do that. So if I go into the drivetrain and I change the code to add it, there's no guarantee that your joysticks didn't just break, right? Because I'm touching code that somebody else is using. So instead of having and changing drivetrain, if I have a child of drivetrain, which is a PID drivetrain, that then implements the ability to move 5 feet. And when it sets the power, it calls the parent's drive methods, right? When I push the button, that code may break, and it may not drive 5 feet. But since I never touched the parent class or the base drivetrain, those joysticks cannot have broken, all right? They are going to work, all right? So anytime you touch code, you can introduce bugs. As a matter of fact, I got a shirt that says 99 bugs on the wall, 99 bugs in the code, 99 bugs in the code, take one down, pass it around, 110 bugs in the code, all right? So if you touch code, it can break, all right? So by instead of changing code, I think of it like a onion. I start adding layers on the outside. So underneath, it never changed. So I have a drivetrain, and I have a PID drivetrain. Maybe I have a motion profiling drivetrain, and you add on top of them so that at no point can you risk the driver's joysticks from breaking. Oh, darn it. The Liskov inversion principle. Objects should be replaceable by instances of their subtypes without altering the correctness of the program. By Barbara Liskov, 1994. This one, the other one's like single responsibility. I get that. Open to extend, close for modification, right? Don't change code, add code. This one's kind of really strange, all right? So if we think about that credit card and check example, right? When those payments got to the bank at the end of the night, they need to take money out of the bank, right? So they can write code that says, if I have a check, I do these things. And I have a credit card, I do these things. With the Liskov inversion principle, you can do it a little differently. We talked about you might have a parent class called a payment, and then a check class underneath it, and then another child class for the credit card. Remember I said how there's the common stuff is at the base? So instead of having code specific to a credit card and code specific to a check, what you could do for taking the money out of the bank, you could have code that works on a payment type, all right? So what the Liskov Liskov substitution principle says, if I have a parent and I pass in a child, the child should not break the functionality of what the parent provided. So one of the things we had in that parent class for the payment was take the money out of the account, right? So by doing that, the way software works is if I have a child, I could pass any method that takes a parent can also take a child because it has all that same functionality. It's just a bigger set of that functionality. And so now instead of being coupled to just a credit card or just a check, you could just say, give me a payment type and I'll take care of it, okay? So you do not want to break the functionality of your parents when you create children. And as a sneak preview, for the 2019 WPI Lib, doing all this stuff is really cool because you could actually test your robot before actually having a robot if you do this kind of stuff. And I'll talk about that at the end. But the key to that is this. Interface segregation principle. If you look at that box up there and you want to plug in your mouse, where do I plug it in at? You have to kind of figure it out. So interface segregation principle says, don't have a bunch of stuff. Have all your interfaces very focused, okay? So doing that means that somebody who's using your class and provides that interface knows what to use, all right? If you have too many methods in your interface, you're probably doing a lot of stuff, and they won't know, do I use this method or that method? This other method or this current one? If you think about it, two of the biggest companies in the world, Apple and Google, they didn't do anything new. You know, there were search engines before them. There were MP3 players before them. But it turns out that when you picked up an iPod, a real simple interface, play, forward, back, stop. That's all there was. There wasn't like seek forward a little bit, go back. The more you have interfaces, the more you have to your interface, the harder it is for the user to understand. So you want to keep your interface focused to what the task is, and it makes people that use your software a lot easier for them to consume it in program. The D in dependency inversion principle is, the D in solid is the dependency inversion principle. So the dependency inversion principle basically states abstraction should not depend on details. Details should depend on abstractions, by Robert Martin. So if you think about a Keurig machine, right? A Keurig machine has their special little cups, right? And if you want to make coffee in a Keurig machine, you have to have their special cup. And if you want to make hot chocolate and they don't make one, you have a coffee machine that the company said, you can't make hot chocolate in your machine. Or if you want this special French blend coffee, you can't make it because it's my machine. I don't care what you want. The dependency inversion principle changes that around. It says it's a coffee machine. I want to put what I want into it, and if it happens to be hot water going through chocolate, I want to make chocolate. If it's tea, I want to make tea. If it's soup, it's just hot water going through something. I want to tell you what I want to be able to make, right? So, Keurig had little sensors, you can only use their cups, and people are like, sorry, you don't get to tell me about what I have, right? So I want to be able to change it. I control what you do, not the opposite way around. That also applies in software, all right? So, for example, when you wire up your drivetrain, you got your motors and stuff. Encoders measure how far you've gone, all right? And you can wire up the encoder into one of two ways. You could put the encoder into the motor controller, in which case the motor controller will tell you how far you've gone. Or you can plug the encoder into your robo-reel, in which case you use a different set of code and talk to the robo-reel to figure out how far you've gone, okay? If you as a programmer decide you want to read it from the robo-reel, you've just told Build they can't change your wiring because of your software, right? So now you're dictating to everybody else how they have to build, okay? Now, if we, instead of having that code in there, we actually had a class that wrappered the encoder that knew how to talk which way, right? So I could have a motor controller encoder class, and I could have a Rio encoder class, both of them inheriting from a base encoder class. And the drivetrain used a base encoder class. You could actually give to the drivetrain which things you wanted to use. So now Bill can say, we didn't have enough wire, so we decided to put it in the CAN bus. We put it on the motor controller, and you're like, oh, easy change, right? I just used a different class. And instead of saying, let me change all my code and go over here, and the other thing is, since you have it in an encoder class, you got a single responsibility, right? If you change that encoder, if you find a bug in that code and you change that code, it's fixed everywhere because encoders now are in a single responsibility, right? So they all sort of go together. So those cover the 5 single responsibility principles. Now I want to talk bigger picture, and this is coming out in the 2019 WPI Lib framework. We are a beta test team for that, so we're playing with it right now, so it's kind of cool. So there's something in the software industry called unit testing or test-driven development, okay? Prior to 2019, if you took your robot code, unless you put a lot of effort into it, the only way to test your code was to put it on the robot and test it. Okay. So now, in 2019, you can start. They made it a lot easier to test your code off the robot. But if you don't write your code in a structured manner, then you're like, it broke. Okay. So I'll give you an example of one of the things that we did last year on 6829. We have a show of hands. Who here uses the command robot for their software? Okay. Who uses iterative robot? Who here doesn't? Iterative? Okay. Who here doesn't know? All right. So I'll talk about the command one for real quick. It's real simple, real simple. You have commands and you have subsystems. Commands have logic, subsystems are your hardware. Boom, you now know the command robot, okay? So we wanted to have when you use the joysticks, the command is running and saying, read the joystick. If I'm going, take the value from the joystick, tell the drivetrain to go that fast. We wanted to make it less twitchy. So they wrote code, said, read the joystick, did some math, and then told the drivetrain to drive that fast. And it turned out they started driving. And they turned right, and it's going right. They finally started turning right faster, and it went left. It's like, what happened there? So if you look at the code, you see them reading the joystick, there's a bunch of math, and then it sends it to the drivetrain. We had no idea what the problem was. We were reading the joystick wrong? Was the math wrong? Was the drivetrain wrong? Because all that code was in one spot, and you could not sort of separate the things, okay? So we did by using the single responsibility principle, right? The logic of the command should be high-level logic, right? So the implementation of all that math is not really high-level logic. So what we did was we said, well, all that math, we came up with an idea of a transform. So that math went into the transform. And the transform name became squared input. So guess what squared input does? It squares your input, right? So when you're closer to 0, it's not so twitchy. As you go further out, it starts getting faster. Great. So now I got it over there. So guess what they did? They wrote, this was last year we couldn't do unit testing. They wrote an application that used just that squared input code. And they went through and they went from -1 to 1, and you could step through really easy. And it says, -1 should be -1. They said, if I give it this, I should get this back. And they found out when they got to from negative 0.01. When I got to -1, it went to 1. My problem is that math was wrong, all right? But since I took that math and put it in its own class, I could test that math. I know that math is right or wrong, okay? All right, so great. So we can make that testable, right? So I got this command. Now it has a object in it that does the math, right? It's got a transform. Well, how do I test the command? Because if I test the command and it breaks, it still may be the math, right? So what I could do is I could create a fake command or a fake transform. So if I have a transform, if I basically do a fake transform that is a subclass of transform, I could give that fake transform to the command, and I could program that fake transform to always return a number. There's no logic; just return 0, right? So I could then call the command. It reads a joystick, and then returns back 0, and then it could pass 0 to the drivetrain. Well, the drivetrain would be screwed up. So we make up a fake drivetrain, right? So I can now have a fake transform and a fake drivetrain. So I read the joystick. I give the value to the transform. I get back 0. The command better give 0 to the drivetrain. If it doesn't give 0 to the drivetrain, it's broken, right? So now, if I have a fake transform and a fake drivetrain, and I pass in the joystick as 0.5. If I don't get 0 out, the only code that's broken is your command, right? Before, it could have been the command, it could have been the math, it could have been the drivetrain. It's all over the place, right? So single responsibility, the command does logic, right? So that was very focused. It's also very cohesive. I use Liskov inversion because I needed to have a transform. So I have a base transform with a different fake transform, but since they're using inheritance, it's a subchild, I could put it in, all right? I don't always want to have fake stuff, so I want to pass into real stuff. So I'm using dependency injection to figure out which one I want to do in production, at competition. I put the real one in. When I'm testing, I put the fake one in. So all of these principles, when you put them together, they really bleed across everything, all right? So you're trying to do your code. Think of your code should be like Legos, right? If you bought a Star Wars TIE fighter and then you took it out of the box and it was made out of Legos and it's all glued together and you got a TIE fighter, great. I want to build an X-Wing. Sorry, it's all glued together, you can't change it, right? Think of your code as bricks. Yes, here's all the bricks. Here's the plans how you make a TIE fighter. Here's the plans how you make this, right? So you want your code to function the same way. Focused and reusable, such a way you can just put them together in a different order and they start working. Since it's focused, it gives you a couple things. Focused code is short. Short code's easy to read. That 20-page method that I had when I first got there may have been perfectly well written, but by the time I got halfway through it, I forgot what I was doing because I'm like, what am I doing now, right? It's very easy to have focus code like, drive full power, right? So I got a drive full power command, and I see it basically says drivetrain, equals full power. Great, I know it works. If it's really convoluted, it's a lot harder. So using all these principles together makes it easier for you to test, makes your code simpler to read, because now you don't have to read the details of how I turn the motors on. There's just a drivetrain there, right? Drivetrain dot go forward 5 feet. When you're looking at the command, you can say, yes, that really works. So those are how they all go together. Any questions about some of the stuff we went over? Okay. if you will, one of the things that Geekspace does is we try to support a lot of different teams, sort of like what the RoboJacks are doing. We're doing it up in Swanee. A lot of our classes tend to be different than the TE sessions. We want to try to do more in depth to train on different things. I know Dunwoody, they came up, we had a 4-session Java beginning programming stuff on how to get your robot to move. So if you will, important HTTPS, if you do HTTP, the page is not going to work because it's going to realize it's WordPress and the thing underneath it says I'm going to HTTPS, but I'm on HTTP. That's bad. So make sure it's HTTPS. Looking for a survey, a couple things, we as a makerspace are getting funding from different organizations to help promote FIRST. So it's basically just demographic information. So it doesn't ask for your name or anything. And then secondly, anything that made sense, that makes sense. Trying to always get better. I always tell our robotics team, if we're doing robotics the way we are today in 3 years, we're probably not learning. So please give me feedback on what you liked, didn't like, or like, hey, I really like this example, or that was kind of confusing. Please give that back. So if you have any other questions, I'll be here.
Thank you, Brian. Yeah, some applause. So like I said earlier, I'm Sarah Storer. This is Brian Carlson. We'll be here next week. Next week is, I think, hardware session? Yeah, probably. Week 8. Week 7. Wow. All right. Yeah, thank you guys for coming, and I hope to see you next week. Same time, same place,